So the next goal for us is to relate these two different values of delta G and then delta G at standard state. How are these two values related to equilibrium? So is there a way that we could go from these to equilibrium? And it turns out yes. So there is a way to do it. So the equation that we need to do that is delta G at the non-standard state is equal to delta G standard state plus RT times natural log of Q. And you're probably like, holy geez, there's a lot of stuff going on here. So let's talk about what's really going on. So delta G, that's going to be the delta G at all conditions. Okay. So it doesn't matter the pressure, doesn't matter the temperature. That's our delta G value. Now delta G naught, this is only for standard state. Okay, and again, standard state, 298 K, 1 atmosphere. Okay, R, that's going to be the universal gas constant. And remember, that's 8.314 joules per K mole. T, that's our temperature. And that's got to be measured in Kelvin. And then Q, if you guys remember back in chapter 15 when we talked about equilibrium, Q is the reaction quotient. Okay. All right. So for a particular reaction at a given temperature, what variables can change? So to answer that question, the temperature can change, delta G, non-standard state, can change, and Q can change. All right. What can we say about delta G for various values of delta G naught, delta G at standard state? And here it is. Delta G will be larger than delta G at standard state as long as temperature and the reaction quotient Q are positive values. Now, temperature, because we're dealing with a Kelvin system, 0 degrees Kelvin is the coldest that you can actually go. So you can't go negative on temperature. So that's good. So it really comes down to Q. Okay. All right. And Q, if you really think about it, you can't really have a negative Q because negative Q indicates that the reaction's going completely in reverse and there's no product. So you're going to have, so that Q should be positive. So as long as both of those values are positive, and theoretically they have to be, you'll be fine. Now at equilibrium, how does this equation simplify? So at equilibrium, we know that Q is going to become Kc. All right. And we know that delta G at equilibrium is going to be equal to 0. So that would allow us to say this, that delta G is equal to delta G at standard state plus RT natural log Q. All right. Now, using the stuff that we know, if I rewrite this equation and I'm going to replace K with Q, delta G naught plus RT natural log of K, this should be equal to 0. So if I solve for delta G at standard state, this is going to be equal to negative RT natural log of Kc. Now this is an extremely important equation. This is actually one of the key equations in thermodynamics. So using those tables, using those thermodynamic tables that we looked at in the last video and solved for delta G, and in the previous videos we solved for delta S and delta H, we can actually find the equilibrium constant for a reaction. Okay, this is extremely powerful because delta G is a measure of the thermodynamic stability of the products versus reactants. This is reflected in the values of K if delta G at standard state is less than 0, then the equilibrium constant has to be greater than 1 and products are formed. Okay. Now, why does the simple equation have delta G standard state instead of delta G? Okay. Now, and it's saying, be careful, the answer is a little subtle. So there's two answers here. First off, at equilibrium, delta G is equal to 0. And that's by definition. Okay. The second answer is this. Delta G is going to be a fixed measure of thermodynamics because it's based on standard states. Okay. Delta G at non-standard state changes with the concentrations as the reaction proceeds. So let me get that down. So delta G at standard state is a fixed measure of thermodynamics because it's based on standard states. So delta G standard state is a fixed value based on standard states. Okay. Delta G, the non-standard state version, changes with concentrations as the reaction proceeds. Okay. And so now we're at a table that actually makes a little bit more sense of what we're looking at. We're looking at delta G, standard state, the natural log of K, and then we're looking at K. So if delta G is less than 0, so it's negative, the natural log of K is going to be greater than 0, which means K is going to be greater than 1, which means this reaction is going to favor product formation. If delta G is positive, okay, that means the natural log of K is going to be less than 0. K is going to be less than 1, which means that the reaction is going to favor reactants. Okay, and if delta G standard state is 0, that means K is going to be equal to 1, and that means you're going to have equal amounts of reactants and products. Okay, and so we can take a look at this table. We can take a look at this graphically, and here it is. Okay. So on the x-axis, we're looking at the total free energies of the reactants and the products. On the x-axis, we're looking at time or reaction progress. So if it's a spontaneous process, okay, starting from pure reactants, the delta G is going to proceed to get more and more negative. So it's going to get lower and lower as the reaction keeps going, okay? Until you get to the point where you're at equilibrium. So you're at the lowest point on this curve. Now, if you go forward after that point, the reaction becomes non-spontaneous. So the reaction kind of wants to keep you at that equilibrium point. So even if you keep making more product, okay, you keep pushing the reaction, the delta G is going to start increasing, which means you're going to have to figure out where you're going to get that energy for that delta G to keep increasing, which means the reaction is going to naturally, hopefully, keep you at that equilibrium part. Okay, so at the top, we're going to see that the reaction quotient is less than the equilibrium value, okay, and that delta G should be negative in the spontaneous direction. If it's non-spontaneous, the delta G value should be positive. Now, if we're at this point over here, past equilibrium, we should see that delta G, that the reaction quotient is going to be greater than the equilibrium, and that delta G most likely is going to be positive. All right, and then at equilibrium, Q is going to be equal to the equilibrium constant. All right, now what can we tell from the slope of the line at various points for each graph. So we can tell delta G, okay, at a point, at a certain point. Now, delta G, not delta G naught, delta G standard state. So the key equation, again, is going to be this, that delta G is equal to delta G at standard state plus R times T times the natural log of Q, okay? And then the other equation that we want to look at is delta G standard state is equal to negative RT natural log of K. All right. Now, how dependent is K on delta G standard state? Well, looking at this equation, T should be constant because you're not changing the temperature for the reaction. R is a constant, so that means that K has to depend on delta G standard state. So it's very dependent. Extremely dependent. Okay. To comprehend this mathematically, let's calculate K for when delta G at standard state is equal to 100 kilojoules per mole. Let's try this out. So here's your equation. Delta G standard state is equal to negative RT natural log K. So if delta G at standard state is equal to 100 kilojoules per mole, this is equal to negative RT natural log K. All right. Now, let's assume that for this to work, temperature is 298 K, which we have to assume because it's standard state. So putting this all together, R is going to be 8.314 joules per K mole. All right. T is 298 K, and we're going to solve for a natural log of K. Now, because 8.31 joules for the R value doesn't match with 100 kilojoules, let's convert that 100 kilojoules to 100,000 joules. Okay, so 100,000 joules per K mole. That's equal to negative 8.314 joules per K mole times 298 K times the natural log of K. Now, if we divide both sides by negative RT, we get that the natural log of K is going to be equal to 100,000 joules per K mole divided by negative RT, 8.314 joules per K mole, times 298 K. Okay. All right. This is equal to, if you solve for natural log of K, that should give you a value negative 40.36. And if you take that value and raise it to E, that's your exponent for E. E raised to the negative 40.36 is going to give you your K value. K should come out to be 2.96 times 10 to the minus 18th. So this is going to tell you that this definitely favors reactant formation.